7.1, the main part of this note, so is 7.2. You do not have to write anything down for 7.1. A lot of these things are on your formula sheet anyways. Okay, if you want to sketch just notes down to yourself, you can. But it's in general. So to find derivatives of trig functions, we must understand them as limits. So for example, the limit as theta. So we deal primarily with theta when we're dealing with angles. When we're dealing with sine and trig, which you guys should be familiar with from Math 30. So sine theta, limit as theta goes to 0 for sine theta is 0, because we can evaluate sine at 0. What I mean by that is, here is your sine graph. At 0, you're at 0. Okay, y, think about the unit circle. At 0, you are on the x-axis, which is 0 for the sine. Sine is y. Okay, so that you can evaluate that. So just like before, if you can plug in the limit, do it. If you can't, then you can't. You have to now do other things. Can you simplify it? Cosine of theta, limit as theta goes to 0 for cosine is 1. Same thing, when you're going to 0, cosine's at 1. Okay, just plugging it in. Okay? So the one that gets a little tricky is when you're looking at limit of theta goes to 0 for sine theta over theta. So we can't do that because we can't plug 0 on the bottom. That's when we run to the issues. So then in this case, we're just going to look and see what's happening on both sides. If you look what's happening on both sides, it's approaching 1, it's approaching 1. So definition, like a 1 there, it's like a definition. We'll just know sine theta over theta is equivalent to 1. Okay, that's on your formula sheet. Don't have to memorize that. Okay, and the trig limit rules. We just did the first 3 trig limit rules. Okay, just 1 second here. Okay, and then continuing, there's a couple of examples of these. So limit as x goes to 0 for sine x over 2x. So what would that limit be? Well, we can't plug 0 in. Okay, but this is what I'm talking about. You got to kind of think about how can I manipulate this. It's really close to sine x over x. Sine x over x is what? 1, right? We just figured that out. How can I make this, so just think about this. How can I make this sine x, or sine x over x? How can I make it be like that? What's that? No? Yeah, 1 over 2, so we can pull the half out, right? Okay, so if we pull the half out, that's all we have to do. Because remember, we said back in when we were doing the beginning of limits, if you do this, we can limit these separately, right? So that's not a problem. So what we know now is limit as x goes to 0, this is just 1/2. It's a constant, right? Limit of constant's the same constant. This is 1. So your answer is 1/2 for this. So you pulled the 1/2 out to use the definition that you had the formula like sine x over x is 1. 1/2 we pulled out, that's the answer. Okay, a little trickier one here. Sine of 2x over x. Now, things get a little bit different when they're actually in with the sign. We can't just pull a 2 out of there. What do you think about this one? So instead of making it sine x over x, we actually want to think, well, let's make this that. Because it's still sine of something over that same something. So how can I make that sine over 2x? What's that? Not by the half. So like, okay, you're right, we'll multiply by a half. So we want to put a 2 in here, right? So essentially, we can't just do it to the bottom, though. We have to do it to the top as well. So we have to go 2 over 2 like that. Because you can't just go to the bottom because you're changing it. So what happens is, now we can slide this in. We have this. Yeah, the whole thing. Yep. Because if you're timesing it by a half, you're now changing the value of that number. So by timesing over 2 over 2, 2 over 2 is what? It's 1, so we're not changing a value. Right, exactly. I see what you're saying, Emma. Like, you can't just times 1/2 though, because that's you could do it if you could do it both sides, but we don't have another side, so we just can't do that, just mathematically speaking. So now we have that there, so you can see the answer is 1, or excuse me, answer is 2, because that's worth 1, right? Okay. Okay, this one gets a little bit more confusing. Sine of 7x over sine of 4x. So essentially, I feel like all of the work they show you on this one is just kind of not really needed. But essentially, it's going to end up being 7/4. But here's kind of the proof for it. Okay, I mean, we can kind of see how that makes sense. So what they do is, if you look in your book with me, like you're just going to break up in like to 2 problems. So you're going to go So what we're doing there, if you're saying, wait, where'd your extra 7x come from? Well, this is what I want on the bottom, right? I want these to match. So then I have to have this on the outside. It's like 2 over 2, 7x over 7x, 4x over 4x. So I'm still not changing things. I'm just manipulating it so that I can make that a 1 and that a 1. Does that make sense or no? So just I have 2 signs, so that's the first thing. That's the first one we've had 2 signs. I have 2 signs, so I'm trying to get this relationship essentially twice. Okay, so I need to get a 7x below here. So if I'm going to put 7x in below, I got to say, okay, well, there's one above as well. I need a 4x below, so there's a 4x above. 7x over 7x is 1. 4x over 4x is 1. Any questions on that? Okay, so now this is where things kind of just break down and they get a lot easier for us. This is 1, this is 1. So now I'm doing, there's no more signs. I'm doing limit x goes to 0 of 7x over 4x. You're saying, well, we still have 0 on the bottom. Not really. Those cancel, right? 7/4 is now a constant, so 7/4 is my answer. Okay. All right. Okay, so cosine x minus 1 over cosine of x. So in general, whenever you see kind of, so with this one here, they're kind of going through the proof of cosine of x minus 1, which I don't really like about this one, but I'm going to, well, that's fine. We'll go through. It's not a big deal. Okay, so we're going to multiply this by cosine of x plus 1 to top and bottom to help get rid of that off the bottom, or excuse me, off the top first. Because we're trying to find a way to get like things to cancel so that x isn't on the bottom giving us 0. That's what we're trying to do. So if you're saying, well, I don't see where it's going to happen, just be patient. We're coming back to an identity. So this right here, if I multiply this out, what is that? Think about difference of squared, right? Cos x squared minus 1, right? Because the middle's going to cancel. This is where it gets to a lot of like trig identities. Do you guys do much of that in 30? I forget. Do you? Couple trig identities, not too much? Okay. So then that one should look familiar, right? Cosine squared minus 1, x squared minus 1, what is that? What's that? Sine, yeah, it's going to be the negative sine squared x. Yeah, they're on there. They're on this. Yeah, so this one would be a form of the Pythagorean identity, the cosine squared x plus sine squared x. If you minus the 1 and minus the sine squared, so that's the kind of thing is you have to kind of recognize so you can see that. Whenever you see a square, look at the Pythagorean one, though. That's just kind of food for thought. Okay, so this would be negative sine squared x. That's what the identity says. This equals that. Okay, and then now we're going to break it up to this over this, and then the other one over that one. See where they put the negative. They put it out in front. It's fine. These all have limits in front of them. So this negative just comes out in front of the limit because it's a constant, so it's not going to be affected. You can keep it in. It doesn't matter. I'm just following the books. And then it's going to be limit x goes to 0, and then another one of these. Like that. Now, does anybody, I know we might have got lost there, but why did I do that? What just happened? Yeah, this gives us a 1. So we finally got rid of that x. All that work was to get rid of this x, because if that's there, we get 0, and we have a problem. Okay? So all of that work that we just did for this whole problem was to get rid of this. Because if I put a 0 there, I get 0 on the bottom, and I'm stuck. Okay? So then this right here is negative 1. Okay? And then you ask yourself, can I do this? Can you put 0 in here? Okay, what is that? Is it going to be 0? So it's still not going to be, essentially, yeah, so it's going to be, so we have negative 1 here. That's going to be 0, right? That's okay. This is going to be 1 plus 1. So 0 over 2, the answer is 0. So difference between dividing by 0 and the answer being 0, right? Okay, so what I did was, again, this was the issue. Once we got this identity, or that formula, whatever you want to call it, we know that's 1, a negative 1. I can actually plug this in. I mean, you can always do the limit if you can plug it in. We couldn't do that in the beginning because of that again. That x was the issue. So then, here, I can put the 0 in. Cosine of 0 is 1, plus 1 is 2. Sine of 0 is 0. 0 over 2 is 0, times negative 1 is 0. Okay, just plugging it in. All right, so that's all we're going to need to talk about 7.1. And now we're going to go right to the derivatives for 7.2. Okay. Okay, yeah, I want to do right to the derivatives here. All right, so a lot of these, again, these are on your formula sheet. I'll go briefly over, again, if you have questions, ask them. Don't just, if I say briefly but you want to talk about it more, I'm totally fine with that. But what I'm telling you is you get this on your formula sheet. So the derivative of sine is cosine. Okay, we're going to talk about y a little bit, but I'm not going to elaborate into a lot of detail. I do have the proof on here. I'll do maybe the derivative for sine, but I won't prove the other one. Okay? Or maybe I will. We'll see. See how it goes. Okay, so if we do the derivative of sine, so this right here is sine. If I do the derivative of that, it looks like this. This is the derivatives graph of sine. Right? Because slope 0, it's at 0. Slope's at 0 for here. The derivative of that puts me down to pi because the derivative of sine at pi is 0. It's the other side. Okay. See here, there's that 0. So, but long story short, the derivative of sine is cosine. That's what you need to know. Yep. So when it changes direction, that means it's a 0 of the derivative graph. So this is the original. See how it changes direction there? That's why that's at 0 for the derivative. Because when things change direction, that's the horizontal tangent, right? And so that's the 0. That's why here as well, it changed direction. That's why it's a 0 there. Okay?
So like, do you mean when it changes direction, like this max right?
Right. Critical value. Okay? So derivative of sine is cosine. So here is the proof of that with using our f of x plus h. Okay? It looks crazy, but it's not too bad. So if we do f of x plus h minus f of x over h, we plug in sine. So sine of x plus h minus sine of x all over h. We're doing the derivative of sine. So I'll wait. Just be patient. So remember, this is what we're taking the derivative of. Okay? So x plus h, you just put x plus h right here. And then you keep the original. Okay? Now if you look, see this right here? Look on your formula sheet real quickly, please. On the sum angle formulas, see there where it says sine of a plus b, the first one, bottom left, angle sum difference formulas. So it says sine of a cos of b, sine of b cos of a. Sine, that's just the first thing, sine of a cos of b, cos of a sine of b. If you're saying what's b, this is a and this is b in the formula. So remember, this is back to our limits proof. So remember, this is how we define a derivative with limits. So we're defining that what the derivative of sine is cosine by our limit proof. That's why I said I don't really need to go over this like super thoroughly, but it's nice to see. Okay, so here's this. So we change that to the formula. Then you'll see that the next thing they did is they kind of lumped these two together. They both had a sine x. And they pulled a sine x out. So you take that out, you have a cos h, a minus 1. Okay, then they broke these up into two limits. Okay, so they pulled the sine x out because the sine x is essentially a constant in this situation. And let's see here. We can't do the h is 0. Oh, okay. Yeah, we can. So essentially, what it's doing is this right here, 0 minus 1. So what's cos of 0? It's 1. So that gives us 0 on the top, right? Okay. And then what is sine of 0? Okay, so that gives us 0 on the top. So essentially what's happening is by having zeros on the top, they're kind of cheating a little bit. They're skipping a step. But it's going to give us 0 here, 1 here. Because this is saying sine of 0, cosine of 0. Sine of 0 is 1, or excuse me, sine of 0 is 0, which makes it go away. Cosine of 1 is 1, which keeps the cosine. For that proof. So they're pulling it out because essentially it's with an x. And so it's kind of like we're taking sine x of this. So it's essentially, I kind of think about it like this. And so those values of sine, so that's why they have the 0 here. Sine of 0 just makes it go away because sine of 0 is 0. Cos of 1 is just 1, so it stays for cos. The thing I don't like is we don't like, they're kind of assuming sorry, Chris, that's not entirely right. Sorry. This is 1. That's what we know. Sorry. We know that's 1. I was saying they're skipping the step because we can't do 0 over 0. We know that by definition is 1. This one is the one they skipped because we just stole this from the problem we just did. The problem we just did, what did we get when we did this one? What did we get just previously? On the 7-1 section. We got 0, right? Remember? We just did this one, we got 0. That's what they did. They stole it from the previous problem. Sine of x times 0, cosine of x times 1, so we keep the cosine. Okay? All right, so, but long story short, this is all you need to know. When you take a derivative of sine, you get cosine. Yeah, we're like over halfway. Okay, so then here, the second one you want to know, derivative of cosine is negative sine. Okay, a little quicker proof there. I'll just let you look at that if you'd like. Pause the video. All right, so let's just go to actually doing some of these. Okay, so differentiate sine of 3x. So the only thing with sine of 3x we have to keep in mind is that with trig we still have to use a chain rule because there is, like, we treat this as like it's in brackets. Okay, so we're going to go derivative of sine 3x is cos 3x times 3. Just like chain rule works, right? Derivative of it and then the derivative of the inside. So we took the derivative of this, which is cos, took the inside, which is 3. So the complete derivative of that would be 3 cos 3x. So you see the second one. Okay, derivative of sine is cosine. I'm not using programming chain rule. What's inside here? This is like in brackets to us. So derivative of sine is cosine. You keep this just like we do with chain rule, and the derivative of the inside of this is 3. So it's just like it's in brackets. Yeah. Because it's bounded. So if you think about cosine and sine, whenever we do like sine of pi, it's the same reason we can't just minus pi off of that. They're kind of like together. So that's just the same thing as, you know, if I have x plus 3 squared, I can't minus a 3 out of there. It's trapped, essentially. Okay? You'll get used to it. So like this one, we're doing chain rule, but there's actually nothing to do because the derivative of x is 1. So this is going to be cos of x plus 2. There's nothing over here because derivative of x is just 1. We don't have to write that. So cos of x plus 2 is all you need there. The 2 is a constant, so that's gone. Derivative of x is 1. We don't need it. If you want to write it for your own good, no problem. And so essentially C is kind of like the definition. Okay, they're not giving you numbers. It's going to be cos kx plus d, and then it's going to be k. The number in front of x is going to be the one we keep. All right, any questions there? Okay, so we'll get some higher exponents here. All right, so I'll do the first one. I'll let you guys try the second one. Maybe I'll do the second one too. Second one just kind of messes people up. So let's look at A first. So y equals sine of x cubed. So hopefully you've heard enough now. Derivative of sine is cosine. We keep the x cubed. We put a 3x squared out here in front. Again, you can put in the back. It doesn't matter. The book's always going to pull whatever the derivative was out and put in front. 3x squared, because that's the derivative of the inside. Okay. I always hated this, and you might hate this. Do you guys remember how, you should have went over this math 30, how this is really that? Sine cubed x is the whole thing of sine x cubed. Okay, just trigonometry writes it up right above the sine. Because again, those things are, like I said, the sine and the x are, married, if you will, but they're like bounded. They won't, you can't just break this off of here. So that cube means the whole thing's cubed. I like to write like this when I'm doing my derivatives because now I can see clearly what I'm taking a chain rule of. I'll drop the 3. I'll take derivative of sine. I'll put it on the outside. Okay, so it's going to be like this. Drop the 3. Sine x stays here. That changes to 2. Derivative of sine is cos. That's the derivative. Questions on that one? All right, I'll let you try to see a little challenge. Let you try to see. So what I would do first on that part C there is I'd write it like this. I'd write it like that. But it still means the whole thing cubed. Okay, so now is where it gets a little bit tricky. You're going to drop the 3. You're going to keep what's in there. Make it a 2. Okay, and then now what? Yep. You kind of have to do it twice because you're going to get cos of what's in here and then what's in there. Do you guys see that? It's kind of like it's a double chain essentially. So you take the derivative of this, what's in here, which is just cos of this. Well, since I did that, I have to take derivatives in here, 2x. So it's a double chain. This derivative is here. This derivative is here. Okay, and then you could put you can put the 2x in with the 3, make it 6x if you want, just to fully simplify, but that's not super important. All right. Couple more here. All right, try that one. So it's a product rule. Try that one. Okay, so all you have to do here is first derivative second. So that's going to be x squared times a negative sine x. I'll put the negative out there. That's the first piece. Plus second derivative first. That's all you can do with that one. You could pull an x out, I guess, but doesn't really help me in this case. No. Yeah, those x's are locked. So just these two. Yep. Okay, so now for the part where, like I said, where you felt like you're doing good, and then we're going to throw implicit. Okay, so we have to solve for y prime, right? So we're going to take the derivative of everything. So remember, we're looking for dy dx or y prime. That's what we're looking for. Okay, you want that by itself when you're doing these. So derivative of sine x is simply cosine x. There's nothing inside to do. But derivative of sine y is cos y, y prime. Because the derivative of the inside gives us that dy dx. And the derivative of the 1 over there is 0. So then essentially, we're going to minus the cos, the cos x, and then divide the cos y. Wasn't that bad. And so that's what your y prime is. Thank you. Yep, thank you. Perfect. Okay. So I want you to focus on this one. I want you to think about what is it asking you? What is it asking you? Find the equation of the tangent line to y equals sine over x over cosine 2x at the point where x equals pi over 6. Yeah, so it's asking us to get the derivative, and we want to look at the derivative at pi over 6. Okay, so unfortunately, you can see what that's going to be. Quotient rule, we have to do quotient rule. Okay, so here we go. Low D high, or wait. No, it's low D high first. I always forget. Yeah. Okay, so cos 2x, derivative of high is cos x, minus high sine x, derivative of cos 2x. That's going to be negative sine 2x 2 all over low squared we're there. So derivative of cos 2x is, derivative of cos is negative sine with a 2x. The chain rule, derivative of 2x is a 2. Is that good? Yeah. Okay, so I want to simplify the top to see what happens up there. So when I do that, I can't put these together. They're different like bases. I'm not even sure. Did you guys call that anything specifically what these numbers are? I don't know what they're really technically called, to be honest. So that's going to be, see that's a negative 2 there, and a negative here, so it's essentially going to be plus. It's going to be cos 2x, cos x, plus sine 2x, sine x. So they kind of look pretty similar. All over cos 2x squared. Oh yeah, we need the 2. Thank you. Okay, so now in terms, do I need to simplify this more? I really don't need to. Now we can go ahead and look at pi over 6 here. Put those in because we can figure out what those values are. So 2 times pi over 6 is really pi over 3, right? So this is going to be pi over 3 we're looking at. This is pi over 6. This is 2 of them, but 2 pi over 3 and pi over 6. And this is pi over 3. What I mean by that is cos at pi over 3, we should know what that value is on the unit circle. So pi over 3 is this one. This is pi over 6. That's pi over 4. This is pi over 3. So pi over 3, what's longer, the vertical or the horizontal? The vertical. So the vertical is the root 3 over 2, the y. The horizontal is 1/2. So if I'm saying cosine, am I asking for vertical or horizontal? Horizontal, right? Cosine's x. So this right here is 1/2. Okay? You can use your calculators. Your calculators will give you 0.5. Okay? But the unit circle, like I said, it's nice if you have a good understanding. So this right here is 1/2. So I'm going to put 1/2. This right here, pi over 6, is just the other piece, so it's the longer now. This right here is root 3 over 2. These are all positive. We're in quadrant 1. Okay, plus 2 times sine of pi over 3. We said that's the bigger one, so that's root 3 over 2. And then the other one's going to be the 1/2. Okay, and the bottom, pi over 3 of cos again. It's the 1/2. 1/2 squared is 1/4. So when you go ahead and put all that stuff together, okay, you're going to get the simplest number you'll get is 3 root 3 is the value at pi over 6 for the tangent. Correct. That represents the slope at pi over 6 of the tangent. Okay, so remember, just back to our old stuff. This is slope at pi over 6. Slope at pi over 6. Okay, and then the rest of the work they had you do is they had you go to figure out what b was. You can do that by plugging pi over 6 here to get a y, and then you can just do the line stuff with your lines. Okay, I think I'm going to stop there because the next one's curve sketching, and we might do that tomorrow for a warm-up. So we'll start there.